Our next speaker from NIOSH is Brent Slaker. Brent, you still there?
I am still here.
He's going to be talking about the use of LiDAR in a slightly different environment, actually underground mines. So again, we're going to see some beautiful images, and please take it away, Brent.
Thank you, Dan. You probably see a presenter view right now, I assume.
Yes, you're in presenter view.
Okay, I think now I'm fixed.
Yes.
Okay, perfect. So thank you, Dan. Thank you also to all the Pit iRise folks for the invitation and everybody else tuning in. I am Brent Slaker, a mining engineer at the Pittsburgh Mining Research Division of the National Institute for Occupational Safety and Health. And yeah, my bio is in that link Dan shared earlier. But I'm going to be talking today about our experience using LiDAR and photogrammetry in underground stone mining. So a little bit of an oddball in a landslide seminar, but I think because we're monitoring ground movements with this technology, that a lot of these experiences and applications have transferable elements to just watching change in the earth. So hopefully that's still applicable and at least maybe a little entertaining. But I'm not going to get into too much of the technical details of mining and more just broadly how we're using it. So I'll go through a few case studies, but they're going to revolve around mostly stationary LiDAR. So we set up a laser scanner on a tripod, going to leapfrog it around a mine. Mobile LiDAR, which is we're attaching this LiDAR to a vehicle of some kind and driving it through a mine as we collect data. And lastly, close range digital photogrammetry, which is reconstructing 3D geometry from photographs, which fortunately Eric talked a good bit about, so I don't have to get into that much. But we're using all of these. I'll go through our thoughts on that. But because every time I bring up photogrammetry and LiDAR, I get asked to compare them or which is better for which application, I'm not going to do that now and just say that it's changing all the time and I can't keep up with it at this point. And oftentimes they're complementary and used at the same time for the same application. But what is important, I think, right now is that there's a pretty big difference between some of these stationary methods and mobile methods, and that you're often trading accuracy and precision from a stationary job when you move to a mobile job, and how fast you do that scan is going to play into it. So we found on our end that it's really important to know your job requirements before you get into it, which I know should be a little obvious, but you're going to get a lot of misinformation as you go into this LiDAR and photogrammetry space about accuracies and precisions, because everyone likes to just report their instrument's theoretical potential rather than the final outcome. So just something you have to be aware of. If you have a very large job, several kilometers, you're probably going to need a mobile solution, but you might not be able to pick up measurements or movements less than a few centimeters if you've got some of these quicker methods. So just a quick aside, and there's going to be a lot of these. It's kind of the point of this talk is just the things we've learned along the way and how we're using it. So the first case study that I've got is the Pleasant Gap mine in central Pennsylvania, and you can see our LiDAR scanner set up there. It's an underground stone mine. For those of you not familiar with underground mining, I'm going to use some lingo here. The top of this mine, the ceiling is, I'm going to call the roof. The sidewalls there, I'm going to call the ribs, and the floor, I'm going to call the floor. So this, just to give you a sense of the atmosphere we are monitoring. What we're doing is collecting that 3D data from this LiDAR, bouncing lasers off the sides of the mine workings and constructing three-dimensional surfaces from that information. And if we do this multiple times, we take a scan, we come back, days, months, years later, scan again, we can start to compare that geometry and see what's changed. And that's at the heart of a lot of what we're doing, is that temporal change analysis. So in this picture, it's from the same mine as a minute ago. You see these red areas, the warmer colors are where material has fallen off, the ribs or the roof. And we can infer that that means it's loading more there. So it's incurring some damage. You might see also some cooler colors, which represents movement into the opening. So that could either be the roof sagging down, that could be material accumulating on the floor. It could just be people walking around. Any change to this geometry is going to manifest in some, something we can color and start to study. But another little segue, the thing that I see pretty often get misinterpreted and something we have to deal with a lot is the, I guess, appearance of false movements when you're looking at this kind of data. So you can see here, I've just isolated a part of this mesh that we created, and you see some warm colors, you see some cool colors, and you can interpret this as an active rib that's seeing some loading, when in reality it's just we've sampled the same rock face multiple times on different days, and we have different data points in our sample. So this is oftentimes just a function of your point spacing in that geometry, and shouldn't necessarily be interpreted as rock movement. And really, I guess the point is, when you're looking at rock surfaces on the centimeter scale, there's a lot of roughness. So this is going to come into play. So another site I'm going to go through is the Subtropolis mine in eastern Ohio. Another underground limestone mine, experiencing a lot of roof falls, failures throughout the mine. And they're not entirely predictable, not reliably predictable, and they happen very large distances away from each other. So doing something very small scale and local, like a stationary LiDAR, wasn't really reasonable for a mine like this. So you see on the right side of the screen here, a mine map with the area we scanned using a mobile solution overlaying on top of it, and that's, I'm going to say 15 or so linear kilometers. Don't quote me on it because it's a guess, but it's a very large area that we scanned there. And the idea is for us, one, can we see the roof failing if we scan this multiple times? Do we see that rock changing? Can we predict anything? Can we learn anything from it? And also, just with the geometry itself, can we start to understand how this rock mass is behaving if we're following the failures just as they appear at one point in time? So when you have a large job like this, something we're still dealing with right now, actually, is the way error starts to introduce itself into your analysis. You've got error in the instrument, you've got error in your registration of these clouds to each other. You've got surveying error. If your known point is a mile away from where you are now, there's probably been a little bit of drift as you've gone along. So there's a lot of sources of error, and when we're dealing with hard rock, a few centimeters is plenty sufficient to cause failure of a stiff rock. So if you're interested in seeing this movement before it hits a few centimeters, the total amount of error in your experiment needs to be far less than that. So it's not just we want to see centimeter movement, so we need centimeter precision. It doesn't work quite like that. You want to well exceed your error threshold for a lot of this. So what we see in this Subtropolis mine, if we're looking at it at a snapshot, a single point in time, on the left here, you see another plan view of the mine, and the red areas are just colored by elevation into the roof. So red areas are places where the rock has fallen out of the roof, and we can see is that snakes around the mine and start to and for where the load is coming from, where it might be in the future, where's this fall trying to run to. And on the right side, you see something that's a temporal analysis where we're looking at the same information, or we're looking for the same information rather, but we're looking at change over time. So here on the right side, again, the red is areas where the rock has fallen out, it's already failed, and the blue are areas where it's sagging down and about to fail. So with this, we can not only see where the failures have occurred, but we can see where they might occur. And it's giving us somewhat predictive information, but also showing us the shape of that failure. So again, we can make some rock mechanics inferences there. Now, at the same mine, transitioning into our last remote sensing method here, photogrammetry, in addition to those roof failures that are happening, there's also an issue with the floor coming up, heaving into the opening and breaking. So with this is fairly visible through cracks on the floor. So the eye is drawn to these cracks. You see there's a problem. That's what you're looking at on the left side of the screen here. And you can see some areas around the crack where we took photos from different angles and reconstructed the scene that's happening on the right. So our goal is to be able to track this floor movement as it heaves up into the opening. So again, cracks, very visible. It's what the eye is drawn to. You're looking at the orientation of these cracks. You're doing your hand waving and explaining what the crack means as far as how the stresses are acting on the rock mass. And then we come in with the photogrammetry, and what we find is that a lot of the movement we're seeing is not in the orientation of the crack. It's about 45 degrees off of it, and there's some heave to the floor. So it's now painting a different picture, and we found out that our hand waving may have been a little bit in the wrong direction. So with these remote sensing methods, I mean, you're picking up information that you're not going to be able to get with traditional point measurement instruments, because one, you're not going to know where to put them, and you might be trying to pick up the wrong thing. So all this leads into, I'm going to call it an unscientific takeaway that I want to impart, which is that with a lot of these ground control problems, if you're getting into a problem area, there's some time that's going to elapse before you recognize there's a problem, typically, and then you're going to start monitoring, and some time is going to elapse before you pick up the movement and confirm your suspicions, and this whole process involves the rock mass moving and getting harder and harder to fix, and there being an increasing cost both in dollars and the risk to people's safety associated with it. So the earlier you can get these monitoring solutions in to where you actually detect the problem, the better your outcome is typically going to be. And you get it in earlier, one, by having something that works over a large area rather than trying to guess where to go, and getting a very precise instrument that doesn't need to move a lot before you've noticed that it's gone beyond the error bar. So that's the takeaway, and I think the big benefit for some of this remote sensing, precise remote sensing. So the last thing I have to say is that there's an elephant in the room when you're monitoring underground, is that I don't have to deal with vegetation, which is a pretty big deal. This is a picture of my backyard in a different season than we're in now, so it's a little more overgrown. But you can't tell there's a hill there. I know there's a hill there because I've almost fallen down it, but it's something that would be hard to pick up with a visual observation method like LiDAR or photogrammetry. So you might have to plan around seasonality on a lot of these surface problems. And also weather. We do deal with fog, dust, and water underground, and I can say it very frequently interferes with data collection, and it's just something you have to work around and try to minimize dust, stay away from wet areas, and hope the fog isn't so bad that day. But those are the big things that I want to bring up so they're not left out, and also to triple check everything. I mean, when you're working with this data, obviously you double check everything you're doing, but I've seen too many times people draw conclusions about moving rock masses when really it's just a a misinterpretation of the data and not understanding your accuracy. So if something conflicts with your best engineering judgment, triple check it. Don't just assume the data's always telling you one story. But I think I'm going to go one more slide. Yeah, I think that's everything I have. So if you have any questions, I might have time now. All my clocks are covered up. But if not, you can always contact me at that email address below. So thank you.
Thank you very much, Brent. We appreciate it, particularly from you. There is one question. It's from Henry Mongrain, says, what type of mineral resource is being extracted in the mine that these photos were taken in? Construction materials. I was unaware that subsurface mining was extensively used for any industry other than coal.
These actually are underground limestone mines that I've shown here, and there are about 110 of them in the United States. 110 or so stone mines. I mean, mining construction aggregates, lime. There are also some, in addition to your underground metal mines, like your gold and zinc and what have you, you've also got salt mines in the country that are underground. And all of these, you can use the same technology in. It's a little bit more complicated when you get into coal because you have additional regulatory restrictions on using cameras and LiDAR scanners. But yeah, this is limestone, and there are a couple hundred of mines similar to this in the United States.
Okay, here's another question from, excuse me, George Strish. I'm from Lackawanna County. We have a bunch of old anthracite mines. Do most all these mines collapse/move over time? Are mines at risk, and are all monitored?
I would say the degree of monitoring of a mine underground varies wildly. And in terms of coal, there is not a lot of remote sensing like this done from underground because, again, the regulatory environment, and it's logistically, it's also very difficult and expensive to mine large areas for extended periods of time. Now, I know a lot of these coal mines certainly cause surface effects as well, subsidence, from active mining or long finished mining that's still settling, and that's I think frequently monitored from a variety of different sources on the surface. But yeah, underground, I would say not much is being monitored from these old anthracite mines. Maybe active ones now. I don't have a lot of experience with them, but not the older ones.
Okay. I like to hope everyone will join me in thanking Brent for a really excellent presentation. I mean, I had no idea this was going to happen when I was a kid, thinking about all these analysis and all this LiDAR and all this data. It's really an exciting time to be watching this stuff develop, and we appreciate you taking the time to tell us about it.
Thank you.